Welcome back to Astronomy 103. Dr. Harbison here again. And today we're going to talk about planets around other stars. Last time we talked about how stars orbit other stars and what we can do with that. And today we're going to talk about planets. Now, this is going to be a lot of material condensed into one lesson. We've learned a lot about extrasolar planets over the years. And that might be surprising because from my perspective, the first planet we knew about that orbited another star was discovered after I was born. Now, for your perspective, most of you are traditional college students, you have never lived in a world where we didn't know that planets orbit other stars and we could name them. So there's a lot we've found out in the last few decades that we're going to have to gloss over. So it could be a whole other unit in a course. Now, what are we going to do is first we're going to talk about how we find extrasolar planets. In particular, why can't we just find them by looking for them? By looking for them, I mean taking actual pictures with our actual telescopes and actual cameras. We have to look indirectly, look for their effect on their stars. And we have two common methods we do that with, the transit method and the radial velocity, or the Doppler method. And we're going to talk about bias. These methods are not equally good at finding all planets. They're going to find certain planets more easily than other planets. And that means we only know about certain planets, or certain kinds of planets. So, all right, let's start with a little history lesson. In 1989, the planet Gamma Cephei AB, so the star is named Gamma Cephei A. It's a member of a multiple star system, so that's what the A is telling us. The little lowercase b is saying this is a planet that orbits Gamma Cephei A, lowercase b because it's a planet, not a star. Now, it was discovered in the data. We'll talk about how later, but retracted. They found it, but then they're like, we're not sure this is a planet. However, once we knew about other extrasolar planets, people went back and said, no, it's really there. Now, HD 114762 was also found, but it was kind of at the margins. It could have been a brown dwarf. It could be a brown dwarf, could be a planet. It's kind of at the boundary of what astronomers think is the size limit. So those were kind of cases where we were finding things that were close to planets. We're finding maybe planets. The first actual planet that everyone recognized was in 1992, and it was another really weird thing that we didn't expect, which you're going to hear about a lot for when we talk about extrasolar planets. These planets, 3 planets, they don't orbit a normal star, they don't orbit a red giant, they don't orbit a white dwarf. They orbit something called a neutron star. This is one of those weird objects I mentioned in passing when I was talking about the HR diagram and things that are star-like that don't go on them. Neutron stars are one of the things you can get when a supernova happens. They're one of the ways, the remains of a star after that has gone supernova. So you really didn't expect to find planets there, and yet there's 3 there. The star was originally called PSR B1257 plus 12, which basically is the short form of its name. The International Astronomical Union had a contest to name some of the important historically significant extrasolar planets and their stars if their stars didn't have names. So the star is now called Lich, and the planets are now called Draugr, Poltergeist, and Phobetor. Kind of ghostly Halloween-y names for a bunch of planets orbiting a dead star. Now, 1995. This is where we finally discover a planet we're sure about orbiting a sun-like star. It's 51 Pegasi b. It's, again, in the same effort that gave us Lich and Draugr, Poltergeist, and Phobetor, it was named Dimidium, and the star was named Helvetitos. Helvetitos because the team that found it were Swiss, and Dimidium because it's about half the size of Jupiter. Now, this planet is still pretty weird. We were looking for planets like those in our solar system, a Jupiter out where Jupiter is, several AU from its star, rocky planets closer in. But Dimidium orbits its star, Helvetitos, at a distance much closer than Mercury orbits our sun, and yet it's in between Jupiter and Saturn size. Astronomers weren't expecting it, which is why we didn't find it till 1995. We could have found it a few years earlier. In fact, multiple teams were working on finding extrasolar planets. So as soon as one team found Dimidium, the other team noticed they were looking at this star too. They could immediately go back and confirmed it. They hadn't looked because, again, they were looking for Jupiters, which take years to orbit. They figured they had years of data collection. Well, this planet orbits every 4 days, so they could very quickly pick it out. Here is a histogram, a graph of how many planets we've announced every year from 1989 with Gamma Cephei AB to the present day, to 2020. I grabbed this plot from earlier April, so to April. 2 big years are when the Kepler Space Telescope released all of the planets the team had found so far. So basically, they had been working on it for several years, and then they announced all of them at once. But you can see several things. Well, first, there's a lot of planets. There's over 4,000 confirmed planets. Every time I teach an astronomy course that touches on extrasolar planets, I always re-look up the number because it's always larger than the last time I looked it up. It's 100 larger from the last time I talked about extrasolar planets, which was last fall. You know, all of those little planets down, you know, looks like there's a few dozen planets we found just in 2020, or rather just were announced in 2020. Now, the other thing we notice is this is color-coded by how we detected them. There's a bunch of different methods, but there's 2 that seem to dominate, the one in green and the one in kind of a salmon pink. So that's the top 2 on the list, radial velocity and transits. You can see radial velocity has been pretty steady for as far back as we can see on this plot. It was how we found Dimidium, 51 Pegasi IB. And transits have only recently caught on in, you can see they really took off in the 2010s, but they have been really successful. So those are the 2 methods we're going to talk about, how we use those 2 methods to find planets. Now they might ask, well, Dr. Harbison, why don't we just take pictures of them? And there's a few problems with that. First, planets are much fainter than stars. You know, you can observe this even out in the solar system. If you go outside on a sunny day, our sun is really bright. And the planets you can see, like even Jupiter and Venus, are much fainter. This is a problem because when we look at planets around other stars, because they're orbiting those other stars, they tend to be pretty close in angular terms. When you put something relatively faint next to something really bright, it's really hard to see. Jupiter is about 1/1000th of the brightness of our sun, and from a nearby star, it would be as if, let's say you stood on one side of, you stood on the 0-yard line in Memorial Stadium, you had your friend take a ruler, go to the other end zone, hold up the ruler. Difference between Jupiter and the sun would be the markings of the millimeter markings on your ruler, on your friend's ruler. And remember, the sun is 1 billion times brighter than Jupiter. And Jupiter tends to be the easiest planet to find. When scientists were considering, can we find planets around other stars, they always consider Jupiter first. It tends to be the easiest one to see for most methods, because it's basically nice and big. Now, one thought was, well, Jupiter is pretty cool now. It gets most of its light from the sun. Its internal heat is pretty tepid. But when Jupiter was forming, like all the planets were forming, it was brighter, it was hotter, because it was hotter. And a bigger planet, a super Jupiter, would be even hotter when it was young. So there's some thought is we could look for planets that are relatively young and see a few if we can block their stars. And we already talked about this when we're talking about planet formation, that we can basically block the stars. We do similar things when we're studying the corona of the sun. We just send something to space, stick a telescope that has an obstruction in the center, what's called a coronagraph, because it's originally used to view the sun's corona, in front of the telescope, and then look for planets. So this picture, I think I've shown you this before, of this Beta Pictoris system. Beta Pictoris is a star. It's relatively young. It's only about 12 million years old, which is young for a star. And it still has the remains of a planet-forming disk. The gas in the disk is cleared out, so this is kind of a super duper Kuiper belt. And to see the disk, we have to block Beta Pictoris. But if we do an even better job of blocking light, we can get even closer to Beta Pictoris, and we see a little star. That star is not a star. It is orbiting Beta Pictoris. We call it Beta Pictoris b. It is a planet. It's about 7 times the mass of Jupiter, and it's about a Saturn distance from Beta Pictoris. So it's kind of, and Beta Pictoris is a bit larger than the sun, so it's kind of a super Jupiter in a super gas giant orbit. So we've done this with a handful of systems, but they're all young planets. They're all much bigger than Jupiter, and we have to estimate their mass based on how we think young planets cool. We're just getting light. Now, on the other hand, we can do spectroscopy on Beta Pictoris b, so we can learn a lot of interesting things, but these are kind of special cases. We only know about like a handful or two. Want something that can find smaller planets and find planets around normal sun-like stars, not really young stars. So we need a method that does not rely on directly finding the planet. So let's focus on using the star, because we can see the stars. Stars are easy to see. We see stars all the time. So first, let's consider light. Astronomers are very good with light. Now, as planets orbit stars, from some points of view, they block the star, just like as stars orbit stars, for some points of view, the stars block each other and you get an eclipsing binary. Now, planets are much smaller, so it's a lot less likely that they're going to block their star. We can see Venus and Mercury blocking parts of our sun occasionally, but that's because Earth, Venus, and Mercury all mostly orbit kind of in a flat plane. And even then, this only happens rarely. The next time we'll see this Mercury or Venus block the sun isn't for another few decades. This is a picture of Venus transiting the sun, which won't happen again in our lifetimes. So we call these, when a planet crosses in front of a sun, a transit. It's not quite an eclipse because the whole star isn't getting covered up, or even most of it, it's just a little bit. So just like with eclipsing binaries, some close binaries are eclipsing just due to random chance. Some planets that orbit their stars are going to transit just by random chance. So we're not going to find every planet with this method, but we can find a good, nice selection of planets. So, all right, what's going on here? Now, this is, again, like an eclipsing binary, which is why I put this lecture here right after our binary lecture. Like an eclipsing binary, we have a view of what's actually going on, and that's in the center picture, and what we're measuring. We're just counting the light. Now, unlike an eclipsing binary, we aren't directly seeing the planet's light. The planet is not directly glowing. So when we look at this, or if we go back and look at Venus, we're seeing the night side of the planet. So the planet is just completely dark at visible wavelengths. So what happens is the planet just covers the star, and that little bit of the star is just completely blocked by the planet. So we see for a Jupiter-sized planet, that's a reduction of brightness by about 1%. And how long it happens depends on essentially the orbit of the planet, how far away it is from its star, how fast is it moving. So again, what we measure is the star sharply decreases in brightness by about a few percent, or less if it's a smaller planet, keeps that level for hours, then returns to its original brightness. So that's what's shown in kind of at the left. Don't worry about the right for now. And what's going on is we interpret this as a transit. The planet is passing in front of the face of the star and blocking some of the light. So here's what actual individual data look like. This is from a program called Exoplanet Explorers, which is what's called a citizen science program, which is you get citizens, people, non-astronomers, to go on the web and help you do science. This particular one was practice finding planets in data sets that astronomers had missed. Now, some of them were simulated planets. They put a fake planet into a real data set to check to see how well people spotted it, but some of them were just showing people things the data set had flagged as maybe planets and having them kind of look at them and try to confirm them, because there's a lot more non-scientists than scientists. So if you can train a non-scientist to do something and convince them, hey, cool, you're helping science, or hey, cool, this is a great way to waste time when you're in quarantine, you know, it helps human resources issue. So this is what so at the left is what 3 different samples of what you were measuring in terms of days. So you can see this lasts about a day. You know, each cut is about a day's measurement of star brightness. And these are lined up so that the transits all happen at time 0. And you can see there's a dip and it shows up in a few data points. Then what happens is the computer guesses at what is the period of this transit, how many times, you know, how often does it happen, and just basically plots all of them on top of one another. It just says, well, this repeats every so many days. I know that, I can just fold it on top of each other. So the right shows that in an overall view and a zoom in on the transit. You can see this one has a depth of about 2%. And it is a Jupiter-sized planet transiting in front of a sun-like star. And it's pretty clear, you know, it's pretty clear that the kind of wiggly yellow line at upper right is telling you this is what we just see just looking at the star repeatedly over and over. We don't quite, because of various factors, we don't always measure the exact same brightness, but it's pretty close, and it's clearly much smaller, that variation, when you're just sampling the star when it's not doing anything, than when you sample the star when the planet's in front of it. So something that's a bit more like Earth and a bit harder and a bit more what people are actually looking for in this thing, it's right here. So again, similar setup. On the right is the individual data where there might be a transit. Computer's done its best job to line them up. Now it's asking humans, hey, can you look at this and see if it's anything weird? This one's a lot shallower. It's only about 1/10 of 1%. So this is a lot more of an Earth-like planet. Now what we can do for a few planets is we can get the primary transit, where the planet's in front of the star. The planet is always the planet is always the one in front during a primary transit, because the planet is always cooler than the star. But during the reverse, the secondary, we still get a transit there, because at that point, based on the geometry, we're looking past the star at the planet. We're seeing the planet's day side, which is lit up. So we can see a tiny drop as the light from the day side of the planet goes behind the star, and we lose that. It's much, much smaller. We've only done it with like a few Jupiter-sized planets. So this is an example of one of those. So where does this method work best on? Well, first off, there's 2 reasons that having planet close to a star is helpful. The first is the closer the planet is, the faster the orbital period and the easier it is to find it. You know, even if you were in a system that could find a Jupiter-like planet around a sun-like star, that transit will only happen once every 12 years, which is really hard to test for, because, you know, most of the time you're staring at the star is not doing anything particular. Then once every 12 years it dims by 1%, and you'll have to see it multiple times to figure out what's going on. You know, that is difficult to do when astronomers generally can't have projects that last most of our careers, with no hope of finding things. So this method is not very good for Jupiter-like planets in Jupiter-like orbits. The other reason is, to get that alignment right, it's a lot easier when your planet is close to the star. A slight misalignment when the planet is close to the star, might mean it's still transiting and just kind of transiting across a little bit across the top. While if the planet is farther away, it might be just straight above the star and we don't see it. Now, the other thing is we want a big planet, a planet with a nice large radii, so it blocks lots of light from the star. We want a small star so that the planet proportionally blocks more light. You know, a Jupiter-sized planet will block more light from a tiny, tiny red dwarf than a big sun-like star or Sirius. So we want a small star. Now, small stars are also faint. So that means we also want the star to be nearby so that its apparent brightness is relatively bright, even if its luminosity is kind of middling to low. We also want to avoid things that can look like transiting planets that are not, which in this case means star spots. If we go back to the picture of Venus, you can see, Venus is right there kind of at the upper left, but there's lots of star spots. Now, our sun spins slow enough that it takes star spots weeks to cross the solar disk, while a Venus transit will happen over a period of hours. So, but spotty stars are just generally bad at getting that nice, as an example, that nice steady measurement of their brightness out of transit. So try to avoid them. So that's the transit method. It's nice, pretty straightforward. Planet just a small fraction of all the planets in the universe block their star's light as seen from Earth, and we can find those planets, and they should be a random sample of all of the planets tracked down with these biases. We're going to find more close-in planets, we're going to find bigger planets, and it's easier to find these around small stars. So we're not going to find that many faraway planets, and we're not going to find very many small planets. So you can do some transit work from the ground. You can grab even a relatively modest telescope like Bailyn Observatory or a student observatory can find Jupiter-sized planets transiting. We can measure a 1% dip in light. But we're really interested in the smaller planets, the planets that are more like Earth. So, and that you have to do from space. There's just too much variation due to our atmosphere to measure a star's brightness to the degree we need it to. So the Kepler mission is a mission devoted to staring at random patches of sky in the constellation of Cygnus and just looking at all the stars constantly and looking for transits. And it found 2,600 planets. And that's just the confirmed ones. That's just the ones that astronomers believe actually exist. There's an equivalent number of planet candidates, things we think are probably planets, but we have to go back and find them in other sets of data, make sure that they are not some of the other things that the data could be. This mission ended a few years ago. Now, what's up right now is called TESS, the Transiting Exoplanet Survey Satellite. While Kepler just stared at one patch of sky and looked really deep and really hard and really constantly, TESS photographs the whole sky in patches, but takes less time to do it. It stares at any one star less. So it's gonna miss it's gonna miss more things than Kepler, but it's gonna get it's catching a broader net. So far, it's been up for a little under a year, and it's found 45 planets to date, but it's still got over 1,000 candidates. So 45 planets are just the ones we've managed to confirm so far. That's the transit method. This is one method, is we look for these dips in star brightness. There's another method, and we use this one first because it's a little less sensitive to the alignment. This is using not directly a planet's effect on the star's light, but the planet's effect on the star's motion. So remember with those eclipsing binaries, the two objects, the two stars, orbited around their center of mass. That's why, and we could even use that to find other stars, that we could find Sirius B because it was shoving Sirius A around before we actually saw it. So we can do the same thing with planets. Now, a planet is much smaller than a star, so it's a lot harder to shove the star around. Your planet is a little toddler while the star is a big adult. So as they circle, the planet makes a nice big orbit, while the star just kind of wobbles back and forth. And we can't see this in space the way we could with Sirius B and Sirius A, because those were closer to equal mass. They were only off by a factor of a few, while a planet can be off by a factor of 1,000. So we can't see the star actually physically move very well. We've discovered one planet by actually seeing the star physically move, and that's only because we measured really, really precisely. But if the star is moving back and forth, coming towards and away from us, then we can invoke the Doppler effect. Remember, the Doppler effect says that if a source of waves, source of light is moving towards you, the waves get blue shifted. All the wavelengths become slightly bluer. If it's moving away from you, the waves get red shifted, or all the light is slightly redder. And if we look at a star's spectral lines, we can measure that. Now, usually the way you do it is you take a bunch of lines and you use them to get an average. So you measure like 1,000 star lines to measure the tiny perturbation of an unseen planet. So let's look a little bit at a model for this. And again, we have a NAP lab. So here is our sun. Here is our Jupiter. I've moved it a bit closer to its star than Jupiter is from the sun. We're at 0.1 AU. Otherwise, this is a Jupiter-sized planet, a Jupiter-mass planet orbiting a sun-mass star. Now the star is wobbling back and forth. We can't see it because it's too small. It is 1/1000th of this distance. So we can't see it in this picture. What we can measure is the redshift and blue shift of the star's light. So over here, the planet is moving towards us, so the star is moving away from us. Now the planet is moving away from us, so the star is moving towards us. So if we go back, this is kind of the picture we get. We get repeated periodic redshift and blue shift. And again, if you want to do the Extrasolar Planets Lab, that is explored in more detail. So we're using gravity to kind of get at this radial velocity, and we're going to explore this in class. So again, let's look at where this works best. First, it works best if the planet is big. If the planet is big, gravity is stronger, it can pull the star back and forth more. It also works best if the star is close in. And one reason, again, is that close-in planet has a shorter orbital period. We're going to see the changes over a shorter time scale, which is easier to do. We're not going to find a Neptune by this method, no matter how massive it is, because the Neptune takes 200 years to orbit the sun. We're not going to look at a star that long. The other reason is that the star is moving faster when the planet is close in. The planet's orbiting faster, so the star has to also orbit faster. And again, you want a less massive star. It's easier for the planet to shove around. You not just want the planet to be massive in general, you want the planet to be massive compared to its star. And since less massive main sequence stars are smaller and fainter, we want the star to be close by so the apparent brightness is nice. Apparent brightness is bright so we can take lots of data about it. We also want stars that have nice clear spectral lines that we can measure, just like we wanted stars without many star spots to do the transit method. We want a star that looks really nice, really clear, so that when we can make these precise measurements. So what have we learned from this? Well, first, both of the two really successful methods work best on big planets that are close in. They work best on Jupiters that are far closer than our Jupiter. Our solar system doesn't have any of those, which did mean there was a slight delay from when we could have seen extrasolar planets and when we did, because people assumed not to look until we could find Jupiter. Now, it also means that in general, we find more Jupiter mass planets than Earth mass planets because Jupiters are bigger, and we find more close-in planets than far-away planets because those are, again, easier to see. This also works best on the smaller main sequence stars, on G and K types. M types red dwarfs have the problem of, they tend to be relatively spotty stars. They tend to have really blurry spectral lines due to the fact that they are cool enough to have molecules, and they also tend to be faint even when they're nearby. So even though a planet would make a nice big signal if it transited an M-type star, or in radial velocity as it make the star rock back and forth or circle back and forth, it can be tricky to see. We have found some around M-type stars, including Proxima Centauri, our nearest neighbor. It seems to have 2 planets. Now this is another chart from the same place. And again, I got these last week, so they're literally fresh off the presses. This is literally our best knowledge as of last week. This chart plots mass versus period of all the planets we know the masses of. A lot of the transits, we only have a radius of the planet. We don't know its mass. So let's zoom in. So I've taken the chart and enlarged it, and I've added four dots. You can see them because they have a little shadow. Those 4 dots are Jupiter, Saturn, Earth, and Venus. So we can see a Jupiter nowadays. We could find a Jupiter mass planet at a Jupiter-like distance from our star. You could maybe even see a Saturn. Saturn's a little tricky because it takes 30 years to go around its star. Earth and Venus are harder. We might actually see a transit of an Earth-like planet at an Earth-like distance, but we aren't going to get a mass. We're just going to get it's about Earth-sized. But you can also see the biases here. You can see most of the planets we know about are within 5 or 10 astronomical units from their stars. Their periods are no longer than maybe 10 years or 20 years. Most of the planets we know about are gas giants. And the ones we do have indirect hints of, while we do know about rocky planets from transits, we don't have a good indication. It's harder to be sure about that without a mass. We found a lot of kinds of planets that don't exist in our solar system. The fastest planet in our solar system is Mercury, which orbits a bit under 100 days, but we found hundreds of planets that orbit have a much shorter period, so they're much closer than Mercury is to our sun, and some of them are quite large. You can see some of them are Jupiter mass. Go back to 51 Pegasi b, Dimidium. It was the first planet orbiting around the sun-like star, and again, it orbited once every 4 days. It was something like 1/20th of an astronomical unit from its star, while Mercury is more like 0.4, so 4/10, 2/5. And it's between Jupiter and Saturn in size. Discovered if you go back to the chart, there's a big section of those. That big green blob at kind of middle left is full of Jupiter mass planets that are very, very close to their stars. Now, we gave them the name hot Jupiters because they're like Jupiter, but very hot because they're close to their star. And this really changed how we thought about planet formation. We assumed prior to this that planets tended to form in the place that they ended up, that Jupiter formed out where Jupiter is now, Earth formed about where Earth is now. But we don't know how to make a Jupiter that close to its star. So the idea is that many of these planets might have formed farther out and migrated inward, that interactions with other planets or with that big planet forming disk pushed them inward. Now, not all planets. I mean, Jupiter didn't move so dramatically because then we wouldn't have Earth. But it's really changed how we think about planets. In 1990, we assumed that our solar system was typical. Our solar system was nearly universal. If a solar system was going to have planets, it was always, they would follow a similar pattern. And now we know, well, our solar system isn't uncommon. It's harder to see. But we found plenty of Jupiter-like planets at Jupiter-like distances. And we're starting to find Earth-like planets at Earth-like distances, though we're still we're kind of far off from that. But there's a lot more other options. So we talked about today, planets are hard to find with imaging because they're cooler and smaller than our star, and they're very close to stars. So even if we block the star, we often have trouble seeing the planet. But we can observe their effects on the star's light via transit and their effect on the star's motion via radial velocity. Now, both of these methods tend to favor big, either massive or big in size, close-in planets, which means that we tend to find hot Jupiters more easily than Jupiters or Earths. And this opened up a door to a bunch of new thoughts about planetary systems, how they form, how they evolve, how they change, and what they're like. And we're starting to reach the stage where we can find planets that will remind us of Earth, Earth-sized and Earth-mass planets at Earth-like distances from their stars. For fainter stars, we can find Earth-sized, Earth-mass planets at a distance where water would be liquid, so at temperatures similar to Earth. Haven't quite gotten there for sun-like stars yet. So next class, we are going to talk about star formation. Since we've talked a little bit about planet formation, now we have to figure out how stars form and also how long they live, and then ultimately how they die.